Hello?
Mr. President, this is the Minister of Agriculture speaking.
Minister, what's the matter?
We're facing a catastrophic agriculture crisis due to climate change resulting in prolonged droughts and extreme temperatures. With cash and stable crop yields down 50% and harvests being wiped out, our people
Minister,
will starve.
I understand the gravity of this situation. Please hold. I have to keep it up together. My country and the world is counting on me, but what should I do?
Hi, we're from OtsA 101, and this is a smash course in bio. And today, we will be diving into a topic that might make you rethink your next seafood dinner. The resilience of the apple snail and how we can use synthetic biology to tackle climate change and food shortage. This might all seem like a joke to you, as you may be asking yourself, why are we talking about snails? Well, let's be honest, when was the last time a snail caused a global crisis? But please, just stay and hear us out. The apple snail, Pomencia caniculata, aren't just any garden variety mollusks. These little critters can thrive in conditions that will make most plants throw in the towel. So these snails can survive the chaos of climate change. Just a thought, sleep on it. Old Jungle hit the nail on the head when he said, "We're not the first species to become so powerful on Earth that we muck up the climate and threaten the planet's biodiversity by altering its climate. However, we're the first species to know what we're doing while we're doing it. Irrevocably, climate change is a big deal, and someone has to do something."
Looks like it's time for our mystery compartment. Ooh, what do we have here? Precisely, this is a synthetic powder protein snail derived from the proteins of golden apple snails. Now you might be scratching your head and thinking, golden snail this, golden apple snail that. What exactly are golden apple snails anyway?
Well, that is an excellent question. So this is what a golden apple snail looks like. If you live in town, especially near aquatic fields, you've definitely seen these creatures running around. Let's go into the thought bubble.
Back in the 1970s and the 1980s, a visionary had an idea and thought that this snail could be the next gourmet delicacy and introduced it from South America to Taiwan, a beautiful island in the West Pacific between Japan and the Philippines. However, it wasn't long before people quickly discovered that these little creatures had the appetite that could rival an 18-year-old at an all-you-can-eat buffet. In response to this catastrophe, various methods emerged to combat this invasion, and this includes hand-picking, death pasturing, field drainage, and water control. But the most commonly of them all is molluscicide, and this includes metaldehyde, nicosamide, and triphonalate acetate. However, spoiler alert, these all proved to be ineffective. Yes, I said it, you're all useless. Now get out!
So how can we exploit and leverage the characteristics that make them so resilient? Upon further investigation, in the heart of the resilience are two proteins found inside the apple snails. Key shock protein HSP70, which can be found inside apple snails itself, and OtsA and OtsB enzymes that help synthesize trilose co-chat proteins, which can be found in apple snails microbiota Spitzery monad Spitzery. Back to us. Our mission is to borrow some genetic tricks from our spongy friends and strengthen our crops to withstand whatever Mother Nature throws in their way. So grab your lab coats, put on your thinking caps, and get ready to cultivate some serious knowledge.
Climate change making food shortages feel like a real-life horror movie, we come up with a prototype that taps into the cold and hot resilience of apple snails.
So I guess you can think of it as found as a gauntlet, where we're basically collecting resistant genes like Infinity Zone. Except in this case, right now we only have two individuals. Who knows, maybe one day we'll have the whole collection.
Since we already identified the two key proteins in the apple cell's resilience, the HSP70 heat shock protein from Pomacea cannula, as well as the OtsA and OtsB enzyme sourced from the microbiota Pseudomonas suteri, here comes the sciencey part where we zip it and cut to the real chase.
E. cannula is eukaryotic, which basically means it has complex cells, while Pseudomonas suteri is prokaryotic, meaning simpler cells. So we actually need two different methods to extract their DNA. For the HSP70 gene, we extracted the total RNA, and then through reverse transcription, we were able to get its cDNA. And we also performed PCR amplification,
which is like pressing copy on your printer.
Meanwhile, we went straight for genomic DNA for our culture proteins OtsA and OtsB from Pseudomonas suteri. Since it's prokaryotic, it doesn't need all the extra steps. We also did PCR amplification to make sure that the gene sequences are ready for plasmid insertion.
Now for the plasmid part. To tackle this challenge, we designed specific plasmid tailored to our needs. For the plasmid design of the heat shock protein, we have the HSP70 heat shock protein, its corresponding IBPA promoter, the DSRD red fluorescent protein, which I guess you can think of it as a reporter gene that emits red fluorescent light and tells us when our target gene is being expressed.
All jokes aside, this won't actually be incorporated into the actual organism, or else we'll see shiny green corn in the middle of the night.
Additionally, we also incorporated the antibiotic-resistant gene kanamycin. This antibiotic-resistant gene is especially crucial because it ensures that only the E. coli that carries the target gene as well as the fluorescent protein survives during the transformation process. And this is very important because without this, we wouldn't know if the selection was successful or not, and that would not be ideal for our project. Similarly, for the plasmid design of the culture protein, we have the OtsA, the OtsB, the EGFP green fluorescent protein, its corresponding CSPA promoter, and also similarly, an antibiotic-resistant gene, ampicillin. These plasmids were then co-transformed into the E. coli strain BL21-DE3, followed by antibiotic selection.
After that, we performed Western blotting, which to make sure that the proteins were actually expressed. And we also checked for the fluorescent under microscopes. And voila!
And welcome with Formosa 101. That was a truly innovation and entertaining presentation. So now we have gotten a guess of your grand prize. What on a horizon for it? Where do you envision Formosa 101 in the next 3 to 5 years? What are some immediate milestones you aim to achieve in the near future?
Eventually, we aspire to develop a vaccine derived from our E. coli and test them on the coffee beans at TGC Coffee. We plan to introduce our vaccine to the market after gaining sufficient data and successful testing in the coffee field, as our climate goal remains to help resolve food shortages by enhancing the resilience of cash crops so that they can continue to thrive regardless of the threats climate may pose in the approaching future.
What specific strategy are you implementing to ensure your agricultural project research a wide audience? Can you outline the key partnerships or collaborations you have established to enhance distribution?
We will continue developing our product and seeking to reduce it to a cost that can be accessible to all farmers and not the worthy ones. Our grand vision is to distribute our product across all corners of farmland in the globe. Initially, we'll focus on regions most severely impacted by erratic temperatures. Once we gain a little bit of traction, we aim to collaborate with esteemed organizations such as the WHO, the UN, the FDA, and agricultural departments in the developing nations. We plan to dismantle those greenhouses because, with our innovative product, they'll be as unnecessary as a snow shovel in July. This little syringe promises to save farmers thousands of dollars, making it a game changer in agricultural resilience.
That is truly fascination talk. Once again, thanks for Formosa 101 and we'll see you never.
Now, you may ask, why does any of this matter? Our project tackles the agricultural crisis, which might seem less urgent compared to global conflicts such as the war in Gaza. However, we must confront a staggering reality that 2.3 billion people, 80% of the global population, face hunger daily, exacerbated by the climate change and conflict, particularly in regions such as Africa and the Middle East. Many of us in this exact venue will never truly grasp the true scope of the situation, the desperation hunger can create, pushing people to unimaginable extremes just to survive, and many more people's lives are hanging by the thread as we speak. This detachment blinds us to agriculture's fundamental role in sustaining life. How can we continue to thrive when the very foundation of our civilization is crumbling and we choose to remain indifferent? Well, we might not have the power to change the world overnight when you boil it down. Science we research exceeds more than just academic pursuit or about what happened in the lab. It is about making a real difference in the world, one plasmid, one project, or one snail at a time. As climate change activist Greta Thunberg once warned us, we cannot change the world by playing by the rules. The rules have to change. Everything has to change, and it all starts today.